Hello everyone, and welcome to your first Advanced Swift tutorial. In this series, we're going to be covering topics that are maybe not used by Swift developers every day, or maybe they're just topics that are a little outside of your general usage wheelhouse. If you have topic suggestions that you think would fit into this series, feel free to leave your suggestions in the comments below, because this series is probably going to be more of a grab bag of different topics as opposed to sort of a progression that you might see in some of my other tutorial series. So yeah, love to hear your suggestions on things you want to hear talked about. So the first thing we're going to be talking about today is pointers in Swift. And the general reason that you would want to use pointers is because you're interacting with some C library or some C code that you wrote. And that's probably, in C you come across pointers quite frequently as the common thing you have to do in C. And so you're probably going to have to know how to use them in Swift if you're going to interact with those libraries. So the first thing we're going to talk about is just memory layout, and this will probably be a pretty brief overview because I just want to dive into pointers a little bit more. The memory layout aspect is not that important, but it is interesting to know about. The pointers are probably more of what you would use on a higher level to interact with C code. All right, so the very first thing, just a high-level overview of memory. We have, in your computer, you probably have 8 gigabytes or something like that of RAM, and if you want to talk to any of that RAM, you have to give it a particular address. So you might be at byte 1,000,002, for example, and maybe you stored a bool value there, and you would want to read it back, right? So that's essentially the idea of memory. You have a bunch of addresses, and I've simplified this sort of address space in this diagram to just 0 through 15. But the idea still holds where I could just say I want to address this particular byte, and then the contents of what's laid out in memory might resolve to a different value depending on what you put there. So maybe you stored an int32, for example, and you could read out 4 bytes worth of space, and you would get back your full int32, for example. If it was just a bool value that took up a single byte, then you would store that there. And just quickly, the difference between bits and bytes, every byte has 8 bits. So when we're talking about memory, we're always talking in byte addressable memory. We don't really deal with addressing individual bits. So for example, a bool would be a single byte. That means it is 8 bits, and that can hold up to 256 values, for example. So if you're not too clear on bits and bytes, that's going to be a different tutorial. But in this, we're really just talking about byte addressable space. Okay, so with this diagram a little bit in mind, let's jump over to some Swift code to see some of it in action, and I think that'll make more sense. So we've got our first thing here where we have a nice little scalar value that we're trying to find some memory information about it. And in Swift, there's this enum called MemoryLayout, which allows you to kind of address some of these values. So let me go ahead and just run this top guy here. And you can see that the int32 has these particular properties. And the 3 properties that are on memory layout that give us some useful information are size, stride, and alignment. Size is relatively straightforward. It's basically the minimum amount of space that you would need to actually use this object. So that's pretty straightforward for simple values like int32, right? Int32 means it's 32 bits, which is 4 bytes. So the size in this case will be 4. Stride refers to how far you would have to move to reach the next int32, for example. So, or really the next space that's available in memory. So if you put down an int32, the stride is saying that you would have to stride to 4 essentially to get to the next available space. Because obviously an int32 takes up 4 bytes, so you're going to have to move at least 4 bytes to get to the next one. Then alignment is a little more tricky of it's a little more difficult of a concept, and I think it'll make a little more sense with a complex value, but kind of a brief summary of that would be how you have to align particular objects in memory for it to be read in the best way possible by memory. And I'll talk a little bit more about that when we talk about the game board example below. Just to show some other cases, if I switch this to a bool and I run this again, you'll see that this is 1 byte, I could try an int 64, and this would be 8 bytes, right? 64 bits, 8 bytes. So you can see though that for scalar values, right, it's just simple types, we can, all the values are going to be the same, right? The size, stride, and alignment are always going to be the same because scalar values are definite, or at least usually along the, and I don't really think there is, I can't think of a scalar value that would be off of a, basically a power of 2, right? So we deal with either 1 byte, 2 bytes, 4 bytes, 8 bytes, that kind of thing. Okay, let's talk about the complex value that we have below. So here is a Swift struct called GameBoard. We have P1 score, P2 score, and game over, which is an int32, int32, and a bool. Now, I'm just going to go ahead and run this, and we'll see what we get here. So the first two things are just finding the individual sizes of int32 and bool. So we get 4 for int32 and 1 for bool. So if I try to do the memory layout on the game board itself, right, kind of putting this complex value into memory layout, we can see that the size is kind of what we would expect it to be, right? It is 9, which is, we have int32, which is 4 plus 4 plus 1, right? 4 plus 4 plus 1 is 9. Then the stride is kind of interesting now. We see that this actually becomes 12. And that might seem a little odd, but the reason for this is that we can only access, we need enough space to access our largest sizes along their correct alignments. So because int32 is the largest size that we have in this game board, and because it takes up 4 bytes, that means that the game board needs to be aligned along 4 byte increments, right? So that's why the alignment, this might make a little more sense now, the alignment here is going to be 4 because it has to be aligned along the largest value that we have. And in this case, that would be int32. And so if we are going to place this memory layout struct in memory, it needs to be aligned along these sizes. And to demonstrate that, I actually have this, the memory layout thing that I created was based on this object, right? So we have this int32, int32, and bool. And so the size would actually be 9, but there's going to be this space in between where we don't actually have anything. And we're going to end up striding till we hit 12, right? That's what our stride value was here. And that's when we would place the next game memory, whatever I call it, game board object, or game board struct rather, in memory. To demonstrate some other aspects of this, here are 2 other diagrams, which is the same sort of thing. And to demonstrate this, I'm actually going to move this bool into the center spot. And you might expect that this would keep everything the same, but it's actually not going to. So I'm going to run this again. And you'll notice now that the size actually becomes 12, which might seem counterintuitive, but I'll demonstrate that. But the stride and alignment will actually stay the same as they were before. Now, to demonstrate this, this is essentially how this would look. And you might imagine that this memory misaligned example would be what you would expect, right? You kind of expect that if we have this int32, then we have this 1 byte for a bool, and then we have this int32. But this very important aspect of alignment for different values, right? The int32s always have to be aligned along 4 byte increments, right? So they're either going to be at 0, 4, 8, 12, 16, etc., right? They have to be aligned along 4 byte addresses. And so this would actually be a misaligned memory address. And what would happen if this was possible in your system, it would actually have to read twice to get the value and then composite it together. And this is actually either expensive or not possible, depending on the system you're using. The memory padding example is really what ends up happening here. So what ends up happening is we need to keep our memory alignment as it is. So because int32 always has to be aligned along 4 byte increments, the actual struct itself is going to be ending up to be a size of 12, right? It's going to end up being 12 bytes wide, which is what we saw when we asked about it here. And the reason for that is because there's going to be some padding on this bool, basically just empty space really, that's going to end up pushing our int32 to be byte aligned with its expected 4 byte alignment. So that's the concept of size, stride, and alignment. Again, size is just going to be the total value, the total size of what the game board's really going to take up when we lay it in memory, and that applies to the situations where we would have padding as well. Then we have stride, which is how far we'd have to move before we can place the next game board if we were, just placing a bunch of game boards down. And then the alignment is the smallest increments that we can have before we have to basically place a next one. So the reason when we had bool back here, right, the reason that this one worked out with the size of 9, but still the alignment was 4, is because we still, let's just go back to this top example to make a little bit of make this have some sense. We would place a value of 9 down, but the point being is that because the alignment is 4, we couldn't just place an int32 on this blob right here, right? Because the int32 always needs to be 4-byte aligned, and in that case, it wouldn't be, because it would be starting at the address of 9, which is not one of the, it's not a multiple of 4, essentially. So that's memory layout. It's not super crucial to understand in just interacting with C code, but it's definitely good to know the structure of how your structs would actually be placed in memory. And if you're doing something that is very space constrained, maybe on some physical hardware, for example, this is something that you probably want to know about, just because you could end up with structs that are larger or smaller depending on the order in which you place your values. Okay, so anyway, with that said, let's go on to, I'm going to delete the code that I had here, and we're going to do our examples. So the first example I have is how we can get set up here. So example 1a. So now that we know about the memory layout stuff, this is something we have to use if we want to use a raw pointer. And you might not always need to use a raw pointer, but these are some examples of how you would end up creating one. And before I dive into the pointers, let's just talk about the memory layout. So here we have this C character. C character is just an int 8 or 1 byte. So the stride's going to be 1, the alignment's going to be 1, and so if we have a count of 4 times the stride, which is 1, our byte count in total would be 4. And so in this case, you'll see that if you have to allocate a raw pointer, we would end up having a byte count of 4, and the alignment would match whatever the C character was in this case, which is 1. So this is why I talked briefly about the alignment, so that you have an idea of why you have to pass that in. Okay, so with that said, let's go back to my little diagram here about pointers. So in C, there are 8 different varieties of pointers. Seems like a lot, but they make sense, I guess, if you cover what they mean. So there's, the way I've broken it up is somewhat arbitrary, but I've broken it up into immutable and mutable values. So an immutable pointer is generally something that you would get back from a result. So this immutable pointer would be able to point you to a location, and you could read from that location, but you cannot change values in any of that memory, essentially. So to change a value or to store a value at a particular address in memory, you would require a mutable pointer in order to do that. So that's the difference between immutable and mutable. The difference between raw, which we see in the second row here, a raw pointer simply understands byte addressable changes. So the raw pointer just assumes that it's going to be dealing with bytes, and that's essentially how it will assume itself if you just use raw pointers. So you're just saying this is the raw pointer, and it's pointing to a particular address, but it has no idea about what contents are actually stored in the memory. And the difference between a raw pointer and the first example that we had up here is that there's raw and then there's typed. So a typed pointer is a pointer that understands the contents of what it points to. And so, yeah, that's the difference there. The buffer pointer is a way of basically representing an array. So in C, for example, you could have a pointer that points to the beginning of an array, and you would treat it as that, the array starts at this address, and then you know that there's maybe 10 items, and then you could just iterate over those items. The unsafe buffer pointer in Swift gives you the idea of that there's a particular count to the object, the pointer that you have. So the pointer would point to a particular address, but the buffer pointer stores the information of how many things are sort of in this array of content, right? So that's the idea of a buffer pointer. It basically treats the contents as an array, and it can understand how you could enumerate over that buffer. And then the unsafe raw buffer pointer would just be blindly iterating over bytes in that case. So it works the same way, where you just say, I would iterate over, however many bytes I have. And that's the combination of the two, right? You have the raw and the buffer, and it's a combination of those. Okay, I think that's general idea with pointers. So we have immutable, which means you can either read or write. Then the raw means that you don't really have a type associated with it. So if it's not a raw pointer, it means that you have a type associated with it, which could be a struct, it could be a scalar value, etc. And then there's the buffer, which is a sort of wrapper concept around the idea that a pointer could point to the beginning of an array, and the buffer pointer itself contains the count information around that. All right, enough of that explanation. Let's dive back into our example here. So we created an unsafe raw buffer pointer in this case, and we allocated the bytes and then the alignment. And anytime we allocate a pointer in Swift, we also have to make sure that we deallocate it. So unlike any other objects, there is no arc or any reference counting done to clean up your pointer. So it's your job to do that. You don't actually have to have this defer block around it, but it is sometimes nice if you're just working in a single scope to know that you are allocating and then deallocating your object. And defer simply means whenever we go out of this particular scope, we're going to deallocate the object. So feel free to not have defer. And in some cases, you don't want to have defer because you might have to return the allocated pointer, for example. All right, let's go to the next example. So the second part of this. So here we have our raw pointer, and we're just storing bytes. So in this example, you can call store bytes, and you can say what the contents of the bytes are going to be. So if you were to store a different value, for example, you could actually specify that, hey, I want to put down an integer, for example, and that would allow you to basically set down what you're trying to set. But in this case, we're trying to keep the same type that we wanted to use originally. So we wanted to use a C character. And the reason for this is because I'm actually going to generate a C string. And a C string is a very simple concept. It's just an array of bytes, and the string ends whenever there's a 0 placed at the end of the string. So pretty simple. Okay, so in this case, we're storing this byte, which is 76, which happens to correspond to the ASCII character capital L. And then if we want to move with this buffer pointer, we can advance by a particular stride. And so we just say we want to stride by, however much. In this case, the stride is just 1, so we're striding by 1 byte. And then we're storing the bytes of this type again, so we're storing the lowercase u. And as you can see, it just kind of continues where I'm just striding by a particular offset. All right, so when that's all done, now we've stored this content down here in memory at these different locations. And now I just want to enumerate over these values. So to do that, I could actually use a raw buffer pointer. We tell it where we start, and then we tell it the total byte count that we're going to have. So obviously we just pass it the original pointer and then the number of bytes that we want to enumerate over. And that's what this enumeration is going to do, is going to enumerate over those bytes. So let's go ahead, and I'm just going to comment this out for a second. And let's run this program to see that we get out what we expect. So as you can see, at byte 0, we get 76, right, which is what we stored here. And then we have 117, 99, and 0, right? So those are the indexes off of the enumeration, essentially. So, okay, let's go to the second example here where we actually bind the memory. So anytime you're going from a raw pointer to a typed pointer, there's generally a way to use a bind something call. So in this case, we have this bind memory to, and we bind it to a type, which in this case is going to be our C character, because that's actually the type that we had all along. And we could have used this type instead of using this raw pointer, but I just wanted to demonstrate the raw pointer a little bit on the earlier examples. And this will demonstrate how we can go from the raw pointer to the type. So we're just saying, let's go to our C character and we tell it the capacity of whatever that is. So as a result, we went from this guy, which was a unsafe mutable raw pointer. And now we can see that we have an unsafe mutable pointer with a C character as our type. So this is a typed pointer as compared to a raw one. And now there's actually a constructor on string to take a C string and print it out. So if I go ahead and run this, we can see that now my final output is going to be my name. So ta-da, that's how we can do that. So pretty simple. We had our raw pointer example, and then we created a buffer out of it. If we wanted to enumerate over values, we just have to tell them how many bytes there are. And then if we are bored of interacting with raw memory, we can use some type safety here and actually bind our memory to the type that we expect. Okay, let's go to our second example here. So the second example is using a C function, and this one is fgets, which is going to be able to read a string, and in this case we're going to be reading it from standard input. So the case here is we are starting with an input capacity of what we want, so we're going to have 30 slots, and we're actually creating a typed pointer this time, which is generally the preferred way if you already know the type in advance. So we're going to create a C character. We're going to allocate 30 C characters worth of space. And then because we called allocate, we make sure that we deallocate at some point. And then we just do this enter text thing that I have, and then we're calling the C function here. So fgets is a C function, and just to show you what you might be dealing with when you type this out. So the types that we have to pass in for fgets is an unsafe mutable pointer of int 8. And we just created that up here. C character is the same as int 8, so I can actually just paste an input. And then we need the capacity, right? So I'll copy that from here. And then we need the where we're reading the input from, and the standard library actually provides you with the pointer to standard input. So there's a standard in here, which is this unsafe mutable pointer to a file, which is what we expect. And we can use standard input like that. Okay, so now let's go ahead and run this. So we can build and run here. And we have this enter text, and now I can type in hello from standard in. And you can see that when we get a result, we take that C string that we get from the C function, and we construct it and print it out. Great. Okay, let's do the last example that I have here. So example 3, and this one's a little more complicated where we're dealing with our own C type. Now, game board is not the one that I showed you earlier in the playground. I actually have a C file here, which is called game board, and it's a simple C struct. So we have this C struct with P1 score, P2 score, and it's got a game board. And then there's a function called create current score text, and it will return for us a const char, which is a C string based on the game board state. So it'll just give me a nice little printout of a game board. And you can see that the text is here with this create current score text function. If you are creating your own C files and you're interacting with Swift, the last thing you have to do is have the bridging header, and generally the Xcode will prompt you to create this automatically. You just have to make sure that you import the header files that you want to expose to Swift. All right, so let's go back to our main .swift file here. And as you can see, we create an unsafe mutable pointer for game board. We allocate 1 space worth of game board. Then we initialize the space to a particular game board. So we want to initialize a score of 20 for P1 and score of 1 for the other. And the very important thing when you're initializing complex memory spaces, so anytime you're doing something that is not a scalar type, right? So a struct is an example of this. You have to make sure that you de-initialize however much you had. So if I initialize it with a capacity of 1, you have to make sure that you de-initialize with this. And the simple way to know this is that if you called initialize, you also need to call additionalize. Similarly to if you call allocate, you need to call deallocate. So this is the order in which you would have to do this. Again, you don't need the defer. If you don't have the defer, you just have to put it after you're done using it. Okay, so yeah, pretty simple there. We're just initializing some memory with a particular game board. And then we call into our C function with the game board pointer that we have, right? So if I just kind of see how this looks, we are expecting an unsafe mutable pointer of game board type, and that's what we have up there. Okay, so let's go ahead and run this and see what we get out. So we can see that, let me just say hello. And here we go, we got our P1, P2 with the printout of the score for P1 and the printout score for P2. Now, the other important thing here to note is that game text is needing to be deallocated. And this is more of a C-ism that you kind of have to know when you actually have to remove a pointer. But in this case, we're going to be getting back a pointer from this function. And of course, it's going to be giving back a pointer that's, ready to be used. So it's our job, right, to deallocate this pointer. And that's just an important thing to note, is that if you are using C functions, you have to be aware that if you're getting a pointer back from them, you are going to be responsible for deallocating that pointer as well. All right, and the last thing here is how we can simplify this example. So this is a lot of code for what is relatively simple, just passing a pointer into a C function. And really none of this is necessary unless the struct itself is going to escape scope. And I'll explain that in just a bit, but let's just do what the simpler example would be. So I'm just going to say let game board, and I'm just going to make a game board. So I'm actually just going to copy this here. So copy that game board, and I'm going to get rid of all this logic because I actually don't need it. The nice thing about this is that I can actually just pass the memory address of this struct into this function. So I can use the ampersand, and that is saying, hey, take the address of whatever the next thing is. So I'm going to say take the address of game board and pass that as the pointer to our create current score function. And if you use let as your trying to think of if you're using let for your declaration of the game board, it's now immutable, so it'll think it'd be an immutable pointer. But what I actually want to do is make it mutable because it's going to be passed in here. So because you don't actually know what's going to happen, so that's why it has to be mutable in this case. Even though technically nothing's really going to change, but you'd have to define that we could make this a const game board, but that's the reason that it's asking for mutability. And yeah, so that's what we're going to get for this this part. So I can just pass the address of this game board and all would be good. The case that this would not work is that if you were passing this address onto something that would take this pointer on for later. So because game board here is probably going to be allocated on the stack, right? And if, let's say we were in a function, we made this game board, and then the function returns itself, that means all the memory from that function is going to be wiped away, right? Anything on the stack is going to be cleared out. So you have to make sure that this game board pointer is not going to be used at some point or later point in time for these cases. So C is kind of inherently just unsafe in many of these ways, and these are just things you have to look out for when you're dealing with it. But I hope that covers all the cases that we would generally deal with, or at least a large majority of the cases that we would deal with if we're talking about pointers in Swift. So as a quick recap, there is a way to do memory layout to figure out all the different types of ways that your structs or simple scalars would be laid out. And then there are 8 different types of pointers, and I think we covered most of those examples in this particular tutorial. So I hope that helps you out with dealing with your C libraries out there, and have fun interacting with C. If you have any other questions, leave your questions in the comment section below, and I will see you guys in another tutorial. See you then.